Okay, we'd like to review this calorimetry problem here and try to solve this. We have a 32.1 gram piece of an unknown metal, and it has an initial temperature of 90 degrees Celsius. And so it's a hot metal, and it's going to be placed in 100 milliliters of pure water at 20 degrees Celsius in a calorimeter. So you might think about what's going to happen there. The unknown metal, the hot metal, is going to cool down, lose temperature, and the water will gain temperature. You'll realize 100 milliliters of water is the same thing as 100 grams of water, since the density of water is 1. The water temperature is going to eventually stabilize at 25 degrees Celsius, so it's going to go up from 20 to 25. Of course, the metal is also in the water, so it will go down from 90 all the way down to 25. And so what we want to do here is figure out the specific heat constant of the metal. So, so we're going to have a calorimeter cup here. Let's see here. We'll have a calorimeter cup, which some of you know is basically a styrofoam cup, and it has some water in it. And this is 100 grams of water, and it's at 20 degrees Celsius. And then we have some piece of metal, and we're going, and maybe have it on a string or something, and we're going to put that metal inside the water. And this metal right now is 90 degrees Celsius, and so it's going to go down. So what we need to think of as kind of an equation is, we know Q is heat. And if we think about the heat at the metal is going to lose heat. So if we write this out, we're going to think about, okay, there's going to be heat, and it's going to be lost. We put a minus sign on it, and it's lost by the metal. So we're going to put a little m down there also. So we have heat lost by the metal, and that would equal what? That would equal all of the heat gained by the water. We have a heat flow from the hot thing to the cool thing. And so the heat lost by the metal will all be gained by the water. So I'm going to have plus gained heat by the water. So we know that there's an equation for Q. Q is MCAT. We have the MCAT equation: mass times specific heat times the change in temperature. And so we're not ever we don't need to really figure out the heat lost or the heat gained by either of these things. We just need to know that they are equal. So we're going to have heat lost by the metal minus Q. It's going to equal positive Q by the water. So we can put in MCAT in for each of these Q's. So this is going to be a negative MCAT lost by the metal, and then a positive MCAT gained by the water. So I'm going to have negative mass, this would be mass of the metal, we'll kind of put little subscripts here to designate it, times specific heat, which would be of the metal, times the change in temperature, which would be of the metal. And that was all going to equal the positive MCAT for the water. So it would be the mass of the water times specific heat of the water times change in temperature of the water. So if that makes sense, we're going to lose heat by the metal, and we're going to gain heat by the water. And these are the MCAT equations for both of those. This is the MCAT lost by the metal. This is the MCAT gained by the water. Right now, the one you could figure out would be this one over here. You could figure out the heat gained by the water because you know all three of these things. But what we want to do is, I'm going to try to go with this concept and kind of derive an equation. I need to figure out what is the specific heat constant of the metal. So that's this right here. So I want to solve and make an equation for that. So I can do the specific heat of the metal would equal all of this. So I have mass of the water, specific heat of the water, change in temperature of the water, and I can divide all of that by these other two things here, which would be a minus mass of the metal, and a change in temperature of the metal. Okay, so what I can do here then is I can now just plug in some things. So the specific heat of the metal is going to equal, let's see what we have here, the mass of the water. Okay, that'd be 100 milliliters of water. That's 100 grams. So I can put 100 grams. And then times the specific heat of the water. Well, I could put in two different units. I think what I'll do is I'll put it in the easier one. 1 calorie per gram degrees Celsius. That would be the specific heat of water. 1 calorie per gram degrees Celsius. And the change in temperature of the water. Well, the water went originally from 20 degrees Celsius up to 25. So it's going to gain a positive 5 degrees of Celsius. And then on the bottom, I still have a minus sign here. And the mass of the metal, and that's up here, 32.1 grams. And then over here I have the change in temperature of the metal. Now remember, a change in temperature of the metal equals final temperature minus starting temperature. That's what change in temperature equals. So my final temperature of the metal is going to be 25. And my starting is 90. So this thing is going to really cool down, which means I'm going to get a negative change in temperature for my metal. It's going to drop minus 65 degrees of Celsius. And that's good because we have a minus here and a minus here. And so that can cancel out to be pluses, and therefore my specific heat constant is going to be positive. We don't want to have negative specific heat constants. If you ever get a negative specific heat constant, you did something probably wrong. So you'll notice that I have grams on top and grams on the bottom, and degrees Celsius on top and degrees Celsius on the bottom. And that leaves me with units of calories over gram degrees Celsius. So I can take 100 times 5, which would be 500, and divide it by 32.1. and divide it by 65, and that will give me an answer of about 0.240 calories per gram degree Celsius. 0.240. And that makes sense because we don't really want anything over to 1, because 1 calorie per gram degree Celsius is the specific heat of water, and there's nothing much higher than that. So in everything that we get in these particular units, we would want it to be less than 1. If it's in the other units, joules per gram degree Celsius, we'd want it to be less than 4.184. In fact, we can convert this real quick if we want to the other kinds of units. 1 calorie is equal to 4.184. That's a 4 joules. And if we do that, multiply this by 4.184, you'll see I have this problem working out to come out to be about perfectly 1 joule per gram degree Celsius, which is a lot less than 4. So that works out pretty good. So this is how you do calorimetry problems. You just need to figure out the heat lost by the hot thing, and that will equal the heat gained by the cooler thing. And if you just set up an initial equation like this with a minus Q equaling a plus Q, then you're good to go. Now we can make this problem a little bit more difficult, but it really wouldn't be all that much more difficult. I mean, imagine the calorimeter wasn't made of styrofoam. Maybe it's made of metal itself, and I could give you the specific heat of that particular metal, and I could give you the mass of the cup. Well, then the only thing that would be different is that you'd have the heat lost by the hot piece of metal that we put in the water would equal the heat gained by the water, plus there'd be heat gained by the calorimeter cup. And we could just do it again. And so we have the mass of the cup times the specific heat of the cup, what it was made out of. And then the change in temperature of the calorimeter cup would be whatever the change in temperature of the water was also. So we can make this into a little bit more complicated problem. Have heat lost by the metal, and that's gained by the water and the calorimeter cup. but it wouldn't make it all that much more difficult, I don't think. So hopefully you understood that problem. We'll QED it.